Hello everybody and welcome back to another video on my channel. Today I will be showing a full guide to energy and pretty much anything that you need to know about energy to understand it in physics. So without further ado, let's move on to the first topic. Now work is inherently force times distance. That's what it is. Times distance. Now, if you've already taken the physics course or you know calculus and you've done it, you might know this as the integral of force with relation to time. But this course is algebra, so not yet. It's time to keep it simple for you guys. So, what does this really mean? Well, this means that if I push a 1 kilogram object, or let's say I apply 1 Newton of force across 5 meters versus I apply 1 Newton of force across 20 meters, the one with 20 meters will take more work, of course. And that also explains why you feel so tired after you push a heavy object or something for longer, or after you're running or doing anything for longer, as moving the weight of your body or moving the weight of anything else inherently requires more work. So that's why people are way more tired after like a 5.5 hour tennis match versus a tennis match that takes like 30 minutes. So that's work. Now, when I was talking about why you're tired and stuff, some people would say, well, that's because you've run out of energy. Now, you can't really run out of energy like that, and that's different. That's for another video, which will happen in the future, I promise. But now you might have thought, oh yeah, you're running out of energy. And that's really kind of also what it is. Energy. This is the stuff that makes things happen. So energy is the stuff that makes things happen. And it comes in many, many different forms. Some of the most common of these forms will be kinetic and potential energy. So let's write these down. Now, of course, there are other types of energy and stuff, but they're much more advanced and we will not be covering them. So this kinetic energy is energy of motion. This is the energy that an object has when it's moving. Like if you have a ball, hit it off a tennis racket, that ball will have a certain amount of kinetic energy. And that's why when I want to hit the ball back on the other side, it takes energy to counteract that kinetic energy that was released off the ball when my opponent hit that ball. Now, potential energy is the energy of position. This depends on where on the earth or in the universe did this energy happen. So, that energy is completely different. That energy is like if I have a ball, if I'm holding it in my hand before I'm going to toss and serve the ball in tennis, that ball will have a certain amount of potential energy because it is a certain distance above the ground or above wherever, our reference point is. So that's why potential energy is the energy of position, and that's why it takes effort to hold that ball. Because if you keep your arms straight and hold that ball for a very long time, your arms will start to hurt from fatigue. Because that you're exerting that energy to counteract the force of gravity pulling your arm and the ball downwards. So that's potential and kinetic energy. But how do we calculate this? You know what it is. Oh yeah, if I throw a ball, that's gonna happen. That's gonna have kinetic energy, and if I hold a ball, etc., etc. But how do I calculate this? How am I supposed to bring this down to a number. So this is where we get into the units for work and energy. This unit is the joule. No, not the crown jewel, not all of that, just Joule. We abbreviate it just J. Now this joule is equal to a Newton times a meter. So that's what it is. That's what a joule is. So, okay, good. We know what our units are. We know this, we know that. But again, I told you that I would teach you how to calculate this. But I only told you the unit. So, let's go to kinetic energy. Kinetic energy is calculated as 1/2 of the mass times the velocity squared. And potential energy is calculated as mass times gravity times height. So now we know what kinetic and potential energy are. And notice how potential energy sort of follows that work thing, where you have the force, where this is the force of gravity, and you have our height, which represents distance. So also, kinetic energy also follows the same work structure, but how and why comes from calculus. And that's not a physics course that I'm trying to create for you guys. I'm trying to make sure that this is more accessible to people who don't know that level of math. In the future though, I will create a calculus-based physics course for those who want to bring their skills to the next level. But for now, we're gonna stick to algebra. So what have we covered so far? We've covered what work is, what energy is, and the two main types of energy, kinetic and potential. We've also figured out what is the unit for energy and work, what's kinetic energy, and what's gravitational potential energy. If I forgot to mention that, this is the gravitational potential energy of an object not that far above Earth's surface. So there we have it. We have everything. Except, I lied to you, we don't have everything. Who said that work is just force times distance? What if the way the object's moving and the force that's being applied on it are in different directions? Then what? Then we have to use an alternate formula, a more general formula, if you will. So the general formula for work is force times distance times the cosine of the angle between them. The reason for this is pretty simple. Let's draw a coordinate plane in this upper right corner that I'm sectioning off over here. So if we draw a coordinate plane with our force and distance, so let's have our force vector be this and our distance vector be this. Or distance, really displacement, not distance. Let's actually clarify that, because as I mentioned in kinematics, that was a very important thing, distance versus displacement. So those two are vectors. And over here, we have our angle between those vectors. Now, if those vectors are pointing in the same direction, the maximum amount of work will be applied, because we're moving the object the most when the force is in the same direction, as all of the magnitude of that force is being pushed in that one direction. But what if it was 90 degrees away from each other? What if instead of that, our distance vector looked something like this? Now that's a problem, because by our definition, there would be zero work. Because cosine of 90, first of all, is 0. And second of all, when you split the force into its components, the component of the force of the, like, if we have our x-axis be where the force is, and then our y-axis would be where the distance is, all the magnitude of that force is going in the x direction, but nothing in the y direction. No amount of magnitude of that force is being put in that y direction in order to create that distance. So work has to be 0. So there you have it, all the formulas. Except I was joking again. We're not done. We need to cover one final extremely important theorem that we will discuss more later in other videos. But the purpose of this is to introduce it to you, as this will be very important in understanding conservation of energy, the thing where it's like energy can't be created or destroyed, and it is very essential also to understanding how all these forces are caused and how all energy is really the thing that makes everything happen, like I claimed in this video. So, what is this called? This is called the work-energy theorem. Now, this theorem states that the work is equal to the change in kinetic energy. Now, kinetic energy, we write this as KE. And we write the potential energy as PE, just so you know for the future. Now, since work is the change in kinetic energy and potential energy looks a lot like work, then it looks like something has to do with kinetic energy and potential energy. Now, when something has to do with kinetic and potential energy, that becomes mechanical energy, and that will lead into conservation of energy. So, now you know what everything that you really need to cover is. The energy, work, what it all is, different formulas, and now you know a very important fundamental theorem that helps with understanding conservation of energy and why this works. Now, again, the derivation for this theorem is more calculus-based, so I will definitely cover it in the future when I go over calculus-based mechanics. So, that's sort of it. Except, no, I'm joking. Just one small thing. If you look at the formula for work, and you realize that force and displacement are both vectors, you'll realize that this is the dot product between the two. What does conservation of energy say? Well, first, let me correct myself. Conservation of energy is a universal law in this universe. But besides that, what we're going to talk about today is mechanical conservation of energy, or conservation of mechanical energy. But right now, you don't need to know that completely. So, what is this? Well, this says that the initial potential energy, which is notated as U, earlier I said PE, but it's also notated as U, plus initial kinetic energy is equal to final kinetic energy, final potential plus final kinetic energy, minus all non-conservative forces doing work. And examples of these would be friction, etc., etc. But for this video, for explaining this topic, we're not going to pay much attention to this, and it's not going to be really used until a little later in this series. So, let's move on to actually applying it. But before we do that, a quick overview of a potential and kinetic energy. This is mgh, and this is, half mv squared. But the thing about this is the reason it says conservation of mechanical energy, because potential energy plus kinetic energy is equal to mechanical energy, or ME. So, there you have it. That's just a quick overview of what the conservation of energy is. Now, it might not seem very complicated or very useful at all, but this can massively simplify your life when you are working with things falling over a distance or on other things. And what better way to show you than to do two examples explaining this same conservation of energy. Alright, this problem says a ball is falling from a height h. Air resistance is negligible. What is the speed of the ball right before it hits the ground? Now, if we were to solve this using regular forces, this would be almost impossible. Because first we'd have to measure, okay, we have the downward force G, there's no air resistance, then the speed gets faster and faster. But then over what time? We'd have to use a large combination of the big five equations. But instead of that, what we can do is we can just use conservation of energy. So at the beginning, since it's at rest, or I should probably add that, starts at rest, that was my intention for this problem. Since this starts at rest, we know that before it was launched, it had potential energy at a height h. So our potential energy would be mgh. And since it's at rest, there's no velocity, meaning no kinetic energy. So our initial mechanical energy is equal to mgh plus 0, or just mgh. Now, next, what we have is our final mechanical energy, mf. Now, since right before it hits the ground, it's essentially at height 0, we're going to have no potential energy. But we're going to have all of that be converted into kinetic energy with our final velocity and our mass. Now, since there's no air resistance or any other non-conservative forces, you can just set these equal to each other. So, mgh is equal to 1/2 of mv squared. Now, solving for this gives us v squared is equal to, canceling out the m's and multiplying by 2 is 2gh, and taking the square root of that gives us the square root of 2gh. And look at how simple that was. But this is where the power, the real power, the real usefulness of this comes in. Since energy can't be created or destroyed, that means we can just put everything in terms of energy. We can solve for anything we want to solve for. Since energy is the one thing that stays constant, we don't have to solve for anything else. We already have a sort of reference frame or a basis to solve everything from. And besides that, it has super deep implications about the universe and how it let all of reality exist and stuff. But that's not completely important right now. I'm here to teach you how you can practically use these concepts. So, there's our first problem. Let's move on to our second problem. Alright, over here we have a block of mass m slides down a frictionless ramp of height h and then goes through a loop of radius r. What is the minimum height h in terms of r that would allow the block to complete the loop without falling off? No non-conservative forces. Now, if you try to solve it with force, there's already a problem. How long is the ramp? How much distance is it carrying? And how much distance is it carrying? And to know that, we need to know the angle. But we don't know the angle, and I'm not about to give you the angle. So, what do we do now? We turn to the other tools in our pocket. Energy. But before you use energy, there is a small bit of force analysis that we have to do. When we draw this over here, when we draw our figure, we have our ramp of height h, Then we have our loop. I know it's not a perfect circle, but assume it's a perfect circle of radius r, and then it goes back down. Now, over here, let me redraw that. So, over here we have our diagram, h and r after I redrew it. So, what we realize is when we're in the loop, it needs to pass through the top of the loop, where the force pulling downwards and away is the strongest, as gravity is the only other force. Now, in order to balance that force, we need a minimum speed that it's going to need to have. So, if we draw another diagram, zooming in on the loop, and we have our block over here, we have its weight pulling downwards, and the normal force going upwards, or the velocity going towards the left, which is our minimum speed. And we have our velocity on the left-hand side. But also, since gravity is the only force, this force must equal the centripetal force, which is the force towards the center. So, then, solving for that force, for the velocity for that force, we get v squared is equal to gr, and v is equal to the square root of gr. So, now that we have the square root of gr and we know our minimum speed, we can use conservation of energy. Since it starts from rest at the top, which also should be assumed, we have mgh is then equal to what we have is at the bottom of the loop, at the minimum speed, so it's going to be 1/2 of mass times our minimum speed, gr squared, plus, since at the top of the loop it's the hardest place to pass, that height is going to be 2r, the potential energy will be mg 2r. Now we know exactly what we need to solve for, and we have everything in this equation. Because we have our initial energy and our final energy, which is our kinetic energy, plus the potential energy at that point. So, solving, canceling out m, and then squaring this, so removing the square root and the square, erasing that, then canceling out g from everywhere. That gets us h is equal to 1/2 r plus 2r. So h then becomes 5/2r. And there you have it, the solution to our second problem, made infinitely easier, literally because it would be infinitely difficult to solve it with forces, as I don't think it would even be possible to solve it with forces. So, there you have it, a true example of why conservation of energy is just so powerful. So, we have this thing where it says calc-based, and we are going to use calculus from the very start. You might have noticed in my work video, I gave a definition of force times distance, or force times distance times cosine theta, as a slightly more general formula. But what happens when that force is not constant? Because this is assuming that force is constant, and that's not always true. Force is pretty much never completely constant. It's always changing. Think about when you're playing a sport or anything. You're not going to be running at the exact same speed for a very long time. Your speed is going to change. You're going to speed up, you're going to slow down, you're going to do a lot of things. You're going to change direction. So, for that, we need something more general. And that's where our good friend calculus comes in. Calculus says, who needs that definition? Let's add an integral onto this. So we have our force, this integral over a path, but that's not necessary. That will be talked about in my actual calculus series. All you need to know for now is it's first times d times r, which is pretty much the distance that we use. And we're not using actual d for distance because that would look a little confusing. So that's why we use f times dr. But this is the integral. That's saying, let's say we have a coordinate plane like this, and we'll draw our force vector and stuff. So over here, now we have our force vector facing this direction for an infinitely small distance r. Now that is where this comes from. Instead of doing differentiation with time, where we do very small intervals of time, we integrate it by distance. So this is at this magnitude and this direction for this infinitely small distance. And then, let's say it changes. Let's say it goes here for the next r, then here, then here, then here. All of these across this infinitely small distances r. And when you calculate all of that, then you get the total work. And that's why this formula is so effective. And if the force is constant and the distance is given, we can just integrate it and we get FD cosine theta. And it's really that simple. Now, another thing you might be confused about of where FD cosine theta comes from, which involves vector algebra, which also I'm trying to refrain from using that much vector algebra, or at least very little vectors in this series. And when we go into calc-based physics, I will use more vectors as they are more foundational and stuff. But for now, you don't really have to worry about that. Just know this is why it is this integral over here. Now, then what we have is energy. And if you saw my video about the work energy theorem, you saw that the work is the change in kinetic energy. Now, this theorem doesn't really prove what kinetic energy is essentially directly, but what it does do is this sets up a very important relationship that will be used in the last step of the proof. But in order to prove this, we will have to use our good old definition of work that we saw over here. Our work is equal to the integral of f times dr. Now, what we're going to do is we're going to differentiate both sides. So, differential of work. Now, you could divide by dr, but we are not going to right now. So, differential of work is then force times the differential of r. Now, this force by Newton's second law is equal to mass times acceleration times this dr. Now, acceleration is equal to the derivative of velocity. So dv by dt times dr. Now, if you learned calculus, you know that these differentials aren't exactly like fractions, and you can't manipulate them like fractions. But what we are going to do is we are going to manipulate them by fractions. And yes, I know this sounds very surprising, but this essentially just comes down to using the chain rule, dr over dt multiplied by dv. Now, by the chain rule, you can get dv by dt is equal to dv by dr times dr by dt. And I showed you in my chain rule 1 how that works. But then when you have multiplied by dr over here, you see what you have over here is you have dr by dt, which is our velocity, and dv by dr, so the differential of v over the differential of r, but then you multiply it by those differentials of r, and that's just like integrating the derivative. So then that essentially means we can cancel in quotations out, but in reality all we're doing is just taking the integral essentially of the derivative. So we get v dv, and that's what this equation is going to use. M times v times dv, and don't worry, it will be covered more in depth in my actual calculus-based physics series or mechanics series, which will come after this more algebra-based mechanics series. So there you have it over there, and now what we can do essentially is we can integrate. It's really as simple as that. So we have the work, integrating the work, then we get mass. Since mass is a constant, we go on the outside. Then we integrate v dv, so m just becomes mv squared by 2 plus c. But we're looking for the change in kinetic energy. Oh, I got you there. I told you that this work energy theorem would come in handy in a little bit, and there we go. Because now the change in kinetic energy is this change in these velocities. And then, so mvivf minus vi squared, because really we're going to be taking the definite integral of this from vi to vf. Sorry if I didn't mention that, but it was not completely necessary. Squared over 2. So removing the change element, you get the kinetic energy is mv squared by 2, and that's the actual formula for kinetic energy. And there you go. That's the proof that kinetic energy is equal to mv squared by 2. Done relatively simply, actually, through calculus. If one were to use algebra for this proof, it's still possible, but it would take a couple more steps and a couple more identities. But for this, all it required was a solid understanding of differentials and calculus and our handy work formula. But I defined kinetic energy. What about the potential energy that we were talking about in our work and energy video and our conservation of energy video? Well, I already did a mini derivation in that video. But if you didn't see it, you can realize that it's just since our weight is mass times gravitation, which is our force, and since work is equal to change in kinetic energy, that means work and energy are pretty much the same thing, and that's what this work energy theorem has been trying to get at. So to find kinetic energy, you just find the work. So that work is just times distance. So mg distance, or just mgh, and that's what our potential energy is equal to. So that is much relatively simpler compared to kinetic energy, but I do feel like the kinetic energy one is still pretty satisfying and very important for people to know, especially if they're doing calc-based physics. But you noticed here, we only covered 2 out of the 3 terms. We covered work, we covered energy, but what about power? So let's start covering power. What is power? Well, power is technically force times velocity, or work over time. But this is just the average power. Just like that work was dependent on that force and the average force over that distance, power is again dependent on this. But forces are not always constant, and work is not always constant. So how are we going to do power? Well, let's say we are going to be taking this work on these small intervals of time represented by these arrows. The distance is an infinitely small unit of time called dt. So, since that little change in work over that time happens, we get power is equal to the change in work over the change in time, and that's essentially what our power is. And another way to write that would be dw is equal to p dt. And from there you can even prove that power is equal to force times velocity using the fact that this over here, dw, is also equal to m times dr by dt times dv, and solving from there. So it is very, very, very interesting to see how this all relates and connects together. And I feel like it is very important to know how power is connected to the rest of these. So there's that, and let's continue the derivation of this. And over here, what we have is this, our dw. So p, reverting it back to a slightly earlier form, we get p is equal to, or p dt is equal to force times dv, and then integrating both sides gets us power is equal to force times velocity. And it's really that simple. And actually, I have another derivation for that. Since power is equal to dw over dt, power is equal to force times, if force is constant, then we get force times dr over dt, and that's velocity. So when it's constant, it's also equal to force times velocity. And it really is that simple. The force vector at the time times velocity. So I know this video is not exactly in the subject realm what we were doing. We were focusing on a lot of problem solving and algebra based physics. But I think once in a while I will be adding these different bonus videos, going a little more in depth about these topics, but not to the level of my future up and coming calculus based physics course, where I talk about all of this stuff in more detail. But I really do think it's important to understand how all of these things, all of these formulas and stuff, which look so random at first, actually are very, very connected to calculus. So if you enjoyed this video or found it helpful in any way, please make sure to like, subscribe, and hit that notification for more awesome videos just like this. So see you in the next one. Thank you so much for watching this video. You guys really are the best part of what I do. See you in the next one, and bye-bye.